So hello and welcome in this video on skewness and kurtosis. So whenever we are studying a data, so we are looking for four major characteristic. That is, first one is the central tendency. Okay, so first measure is measure of central tendency. The second one is a measure of dispersion, and in these two categories, uh, most common measures are mean, which you can represent by x bar or mu, and here the most common tool to measure dispersion is variance, or you can say standard deviation. So sometimes it may be possible that two data sets may have same mean and measure of dispersion, that is mean and dispersion means either this is standard deviation or variance. So dispersion, but they may not have same shape. Okay, so that means it is possible that we may have a data or two datas which vary in terms of shape. Okay, means you have one data set which will have this type of shape. Okay, and you have another data which have this type of shape. Okay, and we have another data or another possible shape which is something like this. Okay, so if you just look at these shapes, so let us call this 1, 2 and 3. So here you can see that in figure 1 and figure 2 we are not having symmetry at all. Means in the first figure you can clearly see that the data is stretched, or this curve is stretched towards left hand side here, and in the second figure the data or this curve is stretched towards right. But when you are looking at this third figure, so the data is symmetrical about this y-axis. So the important thing is, means whenever we are having certain data, we have to calculate certain characteristics of that data, and the first one is mean and the second one is dispersion. Dispersion means we may have variance or standard deviation. These are two very common tools. So it is possible that two datas have same mean or dispersion, even then they may not have same shape. So that means there is a deviation, that is something which is missing, means some extra characteristic we have to study in order to have some idea about what type of shape the data will take when we plot this frequency figure. Now if you so whenever we are dealing with the shape of the data, so we call it the skewness. Okay, so the characteristic which help us to determine the what type of shape we have is known as skewness. So skewness is nothing but uh, it is the study of something which is known as symmetry. Okay, so whenever we are looking for the symmetry, means if you are having this type of shape, means the symmetrical shape, then the data has no skewness, because the skewness is simply defined as, okay, so it is defined as, simply one line definition is, it is defined as lack of symmetry. Okay, so skewness is all about the study of symmetry. So whenever the data lacks the symmetry, means we have the first type of figure or the second type of figure, then we have certain skewness in these two figures. But when you are looking at the third figure, so here the data is symmetrical, so there is no skewness at all. And here we this is the qualitative measurement or qualitative definition of the skewness. But when we have to quantify this, so we can use the movement coefficient of or you can say that beta 1, the beta 1 coefficient, which is defined as mu 3 square over mu 2 cube. So this gives us about idea gives us an idea about the skewness. So when this beta 1 is less than 0, means you can say that negative, we call it that the data has negative skewness. Okay, and when your this beta 1 is greater than 0 or it is positive, so you can say that we are having positive skewness. And when this beta 1 is 0, so this is the situation when we have no skewness. Okay, now before we proceed further, let us discuss what do we mean by negative skewness and positive skewness. So if you look at the first figure, so here this data is stretched towards the left hand side. So this type of skewness, because this shape does not have symmetry, so here we are having the negative skewness. While in the second figure, you can see that the data or the curve is stretched towards right hand side. So this type of situation is when the data has the positive skewness. Okay, while this third figure has no skewness, means there is no lack of symmetry, so means this is the case when the data has no skewness. So in this case we are having our beta 1 is 0. So it is very much clear that this beta 1 is 0 when your mu 3 is 0. Okay, when your mu 3 is 0. And it is very important that here in this formula we have the central moments involved here. Okay, so this is the central moments. Okay, central moments means the moments which we calculate about exact mean. Okay, about exact mean. So this is what do we mean by central moment. So now if you look at this expression of beta 1, so here we are having two moments, mu 3 and mu 2 are involved here, and we know that mu 2 is never negative, and mu 3 is negative, but you are having a square here. So it gives an impression that beta 1 cannot be negative. But This is for the uh, numerical value of beta 1. We provide, okay, the sign, okay, the sign of beta 1 will be same as that of mu 3. Means what this implies? This implies that if your mu 3 is positive, okay, if your mu 3 is positive, so this implies your beta 1 is positive, and we will consider our beta 1 as positive, okay. If our mu 3 is less than 0 or negative, we will consider our beta 1 as less than 0, or you can say negative, okay. So the sign of beta 1 totally depends on the sign of mu 3. And the important thing is that whenever we have to find out the value of beta 1, so we have to find out the second central moment and the third central moment, okay. Now continue in this sequence. We have another measure of characteristic of the data, and that is known as the kurtosis, okay. So kurtosis gives an idea about the peakness of frequency curve, okay. So this gives an idea about the nature of peakness of frequency curve. Means when you are plotting the observation and frequency, then this we have three situations, and so the first situation is that your data will be peaked at your this about this y-axis. We have another possibility that you may have a flat frequency curve, means something like this. This curve is not has a very high height, and the last possibility is that your curve neither get a very sharp peak nor it is flatter one. So we have these three situations that when you are plotting a data or when you are plotting the frequency curve, so we may have these three situations. So again we are numbering this as 1, 2 and 3. So this is the case when the data or when the frequency curve has more height than that of the third one. This third curve is our standard normal curve, okay, in both the situation. Means when you are studying this skewness as well as when you are studying this kurtosis. So this is our normal curve. So this curve does not have skewness, means it is symmetric about y-axis, and moreover this curve does not get a very steep height about this y-axis, neither it get flat about this y-axis, as we can look here in first figure and the second figure. So again this is the definition, or you can say that this is how we can define the kurtosis. But whenever we are try to measure this, okay, so we have to calculate another beta coefficient which we call as beta 2, and it is defined as mu 4 over mu 2 square. Again both the moments involved here are central moments, okay. So both these mu 4 and mu2 are central moments. Means again these moments should be about exact mean. Okay, so these moments are about exact mean. Now when this beta 2 is coming out 3, so this is the situation for this type of curve. Okay, when this curve is a very average height, so this is for this type of curve we have beta 2 is equals to 3, and we call such data as mesocortic. Okay, this is how we classify. So this curve is mesocortic. Okay, now when this beta 2 is coming out greater than 3, our data will be leptocortic. Okay, our data will be leptocortic. So this is the situation when your beta 2 is greater than 3, means when the frequency curve has more height as compared to the normal curve. And last, when your beta 2 is less than 3, so this is the situation when your data is platycortic. Okay, so when your data is platycortic, so this is the situation when our beta 2 is less than 3. So this is how we can measure the kurtosis of any data. Now means if you are given certain data and you have to calculate, here we can have certain remarks that if you have to study only skewness, so for skewness we have to calculate beta 1, which is defined as mu3 square over mu2 cube. So this implies that we need only mu2 and mu3. Okay, if you are looking for the kurtosis of the given data, then we have to calculate beta 2, which is defined as mu4 over mu2 square, and for this we of course we have to calculate mu4 and mu2. But yes, if we have to study both, then we have to calculate mu2, mu3 and mu4, and we know that the first central moment is 0, so we have to calculate all the non-zero central moments in order to discuss the skewness and kurtosis of any given data. So here we illustrate this concept with the help of examples. So let us take our first problem here, and here in this problem we are provided with certain data, and we are taking this discrete data here. So we are having the values of x, which are given as 2, 4, 6 and 8, 10, and simultaneously we are having the frequencies of these observations. Okay, so and we have to study the skewness and kurtosis. Okay, we have to study the skewness and kurtosis. So we have to calculate mu2, mu3 and mu4. So first of all, and we are very much clear that these are our central moments. So first of all, we try to find out the mean of this data, and because this data is symmetric, means we are having observations and their corresponding frequencies. So the formula of mean will be summation xf over summation f. So we have to find out first this xf, means the product of observation with the corresponding frequency. So this will be 8, means when you are multiplying these two quantities you will get 8. Again you are multiplying these two quantities, again we are getting 8. This is 18, this is 16, and lastly we are having 10. So first we will calculate summation f, because here you can see that we need this summation f. So our summation f is coming out 12, while this summation xf is coming out 16. So when you are putting these values here, so this is this mean is coming out as 5, okay, using this formula. Now we will calculate the deviation first, and because we need central movements, so in order to get these central movements we have to take the deviation from the exact mean, which is coming out as 5. We have just calculated it. So these are our observations, and in order to get the value of these deviations we have to subtract the value of our exact mean from each of these observations. So we are getting this deviation as -3, because 2 minus 5 is coming out as -3. Similarly 4 minus 5 is -1, it is 1, it is 3, and lastly we are having 5. Now next we will take the product of the frequency and the corresponding deviations. So this is -12, here we are having -2, then it is 3, 6, and 5. And next we will find out the fd square, fd cube, and fd to the power 4, because in order to get the fourth moment we need this fd4. So when you are calculating fd square, so fd square is coming out as 36, 2, 3, 18, and lastly we have 25. Similarly when you are multiplying again this fd square with this d in order to get this fd cube, so it is coming out -108, -2, it is 3, 54, and 125. Lastly we will find out fd4, and we have, in order to get this fd4 we have to multiply this fd cube by the corresponding deviations. So this is coming out as 324, 2, 3, 162, and lastly we are having 625. So now we will find out the values of course this summation fd is 0. Why? Because this is the sum of all the deviations taken from exact mean, so this should be 0. Next we will find out summation fd square, and this summation fd square is coming out as 84. Similarly summation fd cube, it is coming out as 72, and lastly we will calculate summation fd4, means the sum of all the values available in this last column. So this is coming out 1116. So now we will calculate our second moment, which is summation fd square over summation f. Of course, because we are calculating our central moment, so this should be 0, as you can see from here. Okay, so this gives an idea that our mu1 will be 0. Now mu2 is summation fd square over summation f, so this is 84 over 12, so it is 7. Next we have mu3, so mu3 is summation fd cube over summation f, which is 72 over 12, so this is coming out as 6. And lastly we will find out the value of mu4. so which is summation f d to the power 4 over summation f, which is 1116 over 12, and this is coming out as 93. Now we will calculate our, because we already calculated the central moments, so we directly calculate our beta 1, which is mu 3 square over mu 2 cube, and our mu 3 is, the numerical value of mu 3 is 6, so this is square of 6 divided by the square of mu 2, cube of mu 2, so which is cube of 7, so this is coming out as 36 over 343, which is 0.104. Now in order to get the sign of this beta 1, we have to look at the sign of mu 3, and our mu 3 is positive. Okay, so this is positive, so we will consider this as positive 0.104, and this gives that our data has positive skewness, or our data is positively skewed. Now next we calculate beta 2, which is mu 4 over mu 2 square, and our mu 4 is coming out as 93, and when you are dividing this by mu 2 square, so that will be 49, and this is coming out as 1.89, which is certainly less than 3. So this gives that our data is platykurtic. Okay, so this is how we can study the skewness and kurtosis for a given data. Always remember that the moments involved in the expression of beta 1 and beta 2 are central moments. Okay, but it is not always possible to calculate the central moments, because sometimes you may have the deviation in terms of decimal, and that will complicate the entire process of moments calculation. So let us discuss our next problem, or you can say that next example. So we will consider our next problem, or you can say the problem number 2. So again we are provided with the another data where we are having the class intervals, and the class intervals are 5 to 15, 15 to 25, 25 to 35, then 35 to 45, and lastly we are having 45 to 55. And we are also provided with the frequencies. So our frequencies for these class intervals are 1, 3, 5, 7, and lastly we are having 4. Now because this is the continuous data, so we will consider the observation as the midpoint for each of these intervals. So this is coming out as 10, because 15 plus 5 divided by 2, so which is 10. Next we have 20, then we are having 30, then 40, and lastly we are having 50. So first we will, because we know that in order to study the skewness and kurtosis we need central movement, so first of all we are finding the exit mean, and for that we need the product of x and f, means the observations and the frequency. So 10 into 1 is 10, here we are having 60, next we are having 150, then we have 280, and lastly we have 200. Okay, so from here you will obtain summation f as 20, and summation xf as 700, which gives us the value of our exact mean as summation xf divided by summation f, which is 700 divided by 20, and this gives our mean as 35. And as long as our mean is in whole numbers, we can directly calculate our central moments. So for that we will take the deviation about this exact mean, which is 35. So first value of x is 10. So when you are subtracting 35 from 10, you will get minus 25. Then you have minus 15, then minus 5, next is 5, and lastly we are having 15. Then we will find out f into d, which is minus 25, means the product of the frequency and the corresponding deviations. So this is minus 25, minus 45, then next we are having minus 25, then 35, and lastly we have 60. Okay, so this is how we obtain the deviations. Okay, and we are taking the first product of the frequency and the deviation. Next we have fd square, which we obtain by multiplying the entries in this fd column by d again. So this is 625. Okay, next is 675. What we are doing, we are just multiplying this ft with the corresponding deviation. So 25 into 25 is coming out as 625. Next entry is 675, then we have 125, and next we are having 175, and lastly we are having 900. Then next we are calculating the fd cube, and which is 15625. Then we have minus 10, 1, 2, 5, then minus 625, then 875, and lastly we are having 13,500. Okay, next we will find out the our next column, which is fd to the power 4. Okay, so we are calculating our fd to the power 4. So this is fd to the power 4, and or it will be good if we create a separate column, because that will make the things easy to understand. Okay, so we are creating a separate column containing fd4, and in this fd4 we are having first entry as 390,625, then the next value is 151,875, then we have 3,125, next is 4,375, then last value is 2,02,500. Okay, so from here we will obtain our summation fd as 0, summation fd square as means the sum of all the entries available in the second column, which is 2500. Then we have summation fd cube, which is minus 12,000, and lastly we have summation fd4, which is 752,500. So now we are in a position to calculate our movements. So first movement is mu1. Of course that will be 0 because summation fd is 0. Our mu2 will be summation fd square over summation f. So our summation d square is 2500 divided by 20, and this gives our second movement as 125. Now next is mu3, and mu3 is summation fd cube over summation f. So summation fd cube is minus 12,000, and we have to divide this by 20. So this gives you the value of mu3 as minus 600, and lastly we have to calculate mu4. So that will be summation fd4 over summation f. So that will be our summation fd4 is 752,500 divided by 20. So this gives your fourth movement as 37625, and now we are in a position, because we have all the central movements, so we can calculate beta 1, and our beta 1 is mu3 square over mu2 cube. So mu3 square means minus 600, or you can say that we will consider only the numerical value here. So you can consider this as minus 600 whole square divided by mu2 cube, and our mu2 is 125. So this is 125 whole cube, and this gives you the value of beta 1 as 0.1843, which is again positive. So you have positive skewness in this case. And lastly we will calculate beta 2, which is mu4 over mu2 square. So this will be 37625 divided by 125 whole square, and the value which we obtained is 2.408, which is certainly less than 3. So we have positive skewness in this case, or in this example we have positive skewness, and because this beta 2 is less than 3, so our frequency curve will be plate equated. Okay, so this is how we can study about the skewness and kurtosis. These two are another two important characteristics of certain data and help us to distinguish between two different types of data. So before we end this video, let us discuss let us make certain remark, and that will be that the sign of beta 1 will be same as the sign of mu3. Okay, and the second important remark is to calculate beta 1 and beta 2, we need central movements. Okay, so means whenever you do not have the central movements, okay, so you have to use the conversion formula. Okay, and you have to convert the non-central movements into central movements. by using the conversion formula, which we already discussed in our video on movements. Okay, so for this video, that's all.